All right, want to go to the next slide?
All right.
Awesome. All right, well, good morning, everyone. Thank you for joining us. My name is Sarah Husky with 3C Ren. I've started recording this course, which will be posted on our on-demand page. We are here today to talk about recovery ventilators with Nick Brown from Build Smart Group. But before we get going, I just have a few slides to run through. So we ask that everyone just make sure that they're on mute throughout the duration of the course. If you'd like to verbally participate, please raise your hand in the participant section and we will call on you to unmute yourself. We also highly encourage you to participate and ask questions through the chat box. Next slide.
There we go.
So a few words about who we are for those of you who might be new. We are the Tri-County Regional Energy Network, also known as 3C Ren. We are a collaborative partnership between the counties of San Luis Obispo, Santa Barbara, and Ventura, working to improve energy efficiency in our region by offering free programs and services for building professionals and households. 3C Ren is funded by ratepayer dollars, which are collected through the public goods charge found on our utility bills. The benefit of being ratepayer funded is that there is no cost to those we serve, and we are able to return these dollars back to our local economy, which has historically missed out on some of these funds. 3C Ren currently offers 3 programs.
That's my cue, right?
Yeah, thank you. The first program is the Energy Code Connect program, which serves building professionals by offering Title 24 support for everyone from plans examiners and inspectors to architects and contractors. Within the Energy Code Connect program, we offer our Energy Code Coach service, which is an over-the-phone, online, and in-the-field support for Title 24 related questions for both residential and non-residential projects. We also offer trainings and online courses like the one that you are all in right now. Next slide. Another program we offer is building performance training, which serves building professionals such as architects, engineers, contractors, and real estate professionals by offering technical and soft skill trainings relating to building science principles, high performance buildings, marketing and communication techniques. And our third program is our home energy savings, which incentivizes contractors and helps residents save money and make their homes healthier with energy efficient upgrades through incentives and rebates. And with that, I'll pass things over to Nick from Build Smart Group.
Thank you, Sarah. And first, let me say what a privilege it is to work with you, Sarah, most of all because you got all these fine people to show up this morning. A lot of you out there, it is so cool. I created a brand new look for this brand new class today. And, you know, like all things new, it's super exciting to teach a new class. This was developed for 3C Ren at their request and a topic I'm really passionate about. I'm calling them recovery ventilators because, my gosh, calling them heat recovery ventilators and energy recovery ventilators is a mouthful and confusing. We'll talk about the H versus the E as we get started today. So collectively, we're going to call them recovery ventilators. Me being an energy consultant, we're going to talk a lot about the energy implications and potential savings of them, compliance credit in Title 24 as well. But you see, I started with a really happy family image here because to me, they're just as much about comfort and indoor air quality and health and performance as they are energy. And we're going to talk about that whole thing today. And thanks, Sarah, for monitoring the chat as we get going. I'm going to close that out. All right. So you're looking here at my house in Climate Zone 6, just south of the 3C Ren territory in Long Beach. It was a 1950s remodel, the front house, and we recently added an ADU above the garage on the right side of your screen. Both of these houses, you're looking at an HRV and an ERV in this building. So I am practicing what I preach with regards to RVs, really believe in the technology. And my house is a working lab of sorts to evaluate how they perform. We'll talk more about that. But I'm an energy consultant, a KBEC member, a KBEC board member. I do 200-ish Title 24 compliance projects a year, and I teach classes for Energy Code ACE and SCE and PG&E and now 3C REN. This is my first class for 3C REN too, so excited about that. And really like the teaching aspect because it allows me to bring the learnings to a wider group rather than just individual project impacts. Okay, so what I thought we'd organize around is this agenda. Start with recovery ventilators. They are indoor air quality appliances and HVAC energy savers in one. We'll talk about why mechanical ventilation is required and how much of it, how recovery ventilators work, the energy savings possible with them, the compliance credit possible with them, and then if we're going to be incorporating RVs into our projects, it's not enough just to put them in the CF1R, the Title 24. We need to understand how they actually get installed. And so I'll give you some tips on how to specify them and make sure the job gets done. And I want to thank SoCal Gas and Small Planet Supply, which was the genesis of this project, this class. They sponsored research, energy modeling project on recovery ventilators to look at how much energy they can save by climate zone in various building types with various HVAC systems. And I'd like to give a special shout out to Luke Morton for his help with that project. Many of you know Luke. He's a guru and was instrumental in especially evaluating the summer cooling bypass function of these. We'll talk more about that. But boy, this is a remote class and we're all frustrated by not being together in a room. And so I thought we'd use Slido to get a little bit more engaged with this content. For those of you who aren't familiar with Slido, it's a really easy app that you can pull up on your cell phone while we go through the class or in a separate browser window. And it just allows you to answer questions, to throw out comments in word clouds as we go through it. So please, you can either use your cell phone in this QR code to connect to our Slido polls, or type it into a browser window right now. And if you could do it right now, that'd be great because I'm about to do our first Slido interactive experience. All right, hopefully you were able to navigate there. So what do you think of when I say heat recovery ventilators? This will give me an idea of how many of you are familiar with them, and if so, how much, and are you using them? Let's see what comes through here. Plus, it'll just give us a nice orientation start to the platform. Outside area, energy exchange, energy saving. Yeah, part of an electric conversion maybe. Used for Title 24 compliance, balanced ventilation systems. Clean air saved energy, well put. Makeup air could be a makeup air solution too. Okay, good. That helps me know where we're coming from. And it sounds like you guys understand the concept pretty well. So with that understanding, maybe I can go into a little more depth here today. A couple more people typing. We'll just let those pop in because this helps me tailor my comments to what you guys are especially interested in. Air quality, thank you. That's a big part of it, in my opinion. Okay. So I used this tagline. I'm just gonna admit the people in the waiting room. Um, Live better, sleep better, work better, and let your HVAC run better. To put in, this is a tough topic to really capture succinctly, and that was my best attempt to do it. They really are, I think, about improving how you perform during your sleep, if you have a home office, um, and they're helping your HVAC system run better. So hopefully you like that as a summary. So let's start with why we should be considering recovery ventilators. First and foremost, they're indoor air quality solutions. They provide continuous mechanical ventilation for our indoor spaces. And the reason mechanical ventilation is important is it dilutes pollutants and thus enhances indoor air quality. We'll talk more about that concept. They're much better at ventilating a house or a building than spot ventilation fans like bathroom exhaust fans. Yet bathroom exhaust fans are typically the solution that most projects use for indoor air quality. And I would argue that they're vastly insufficient to really ensure good IAQ throughout a building. They also keep neutral pressure in a building. Neutral pressure is important because anytime you have a pressure imbalance across the building envelope, it's an opportunity for indoor air quality problems. You can assume with an exhaust fan running in a building, negative pressure in the building, you're sucking in outdoor air in an uncontrolled way from various places at various times when you may not want that outside air coming in an uncontrolled way. So really neutral pressure allows for enhanced control of indoor air quality. Then we've got the energy savings perspective. This is the part the energy code cares about, but it's just one of 4 categories of benefits that I'm presenting to you today. And they create energy savings by tempering the incoming fresh air that we're required by code to bring in using the outgoing stale air heat. This reduces the burden on our space conditioning system. We'll talk more about how. But the third and fourth reasons to consider recovery ventilators, energy code compliance. And I see a few energy consultants on here today. Recovery ventilators are one of the most powerful tools we have for achieving compliance credit, often an average of 10% benefit because of the energy savings that they can generate. So by using these systems in your energy models, you can compensate for features that aren't meeting code. You can allow for extra glazing, which is one of the main reasons these systems end up making their way into my energy code compliance models. And health. These systems can boost ventilation when needed. Maybe you've got a sick person in a bedroom or you've got people over in a full house. They allow for boosting ventilation, whereas most mechanical ventilation systems are just one speed all the time. And by getting the fresh air behind closed bedroom doors into home offices, by exhausting stale, moist air from bathrooms and kitchens, it allows you to perform better. Talk more about that. Now back to Slido. So if you can go back to your cell phone or your browser window, you should have seen this question pop up now in that same window as before. Tell me, what's your experience level with these systems? A lot of you frequently use them. One or two projects. I kind of thought that would be the majority answer, um, along with never used one before. Okay. Thank you. That helps. So let's lay a little bit of groundwork before getting into the energy savings and compliance credit possible with recovery ventilators, and talk briefly about mechanical ventilation, why it's required, et cetera. And thank you, Sarah, for posting the link to the SoCalGas study.
Yeah, no problem.
So why do we need mechanical ventilation? How do we do it, and how much? First, understand that indoor air quality in a building is not just mechanical ventilation. It starts with source control. By that, we mean VOC-free paints to introduce fewer pollutants into our indoor spaces in the beginning. We mean, like houses you visit where they leave the shoes at the door. That's another form of source control because you're not tracking in whatever you just walked through outside. Not storing chemicals in the kitchen, another example. And all electric trend, the trend towards all electric homes is a form of source control too, because we're not combusting gases in our indoor spaces. Thus, that's one less pollutant to worry about. So we start with source control. And then the second step is dilution of the pollutants, because pollutants are going to be present in our buildings. Mechanical ventilation is constantly bringing in outdoor air, assumed to be fresher and less polluted, and diluting what's happening inside with it. Because whenever we cook, whenever we shower, we're creating moisture, and excessive moisture is one, pollutant that can lead to problems in our indoor spaces. We're creating VOCs when we cook, right? Maybe we just bought furniture from IKEA, or well, IKEA is a bad example because honestly, they're pretty good environmental stewards. But a new foam mattress, let's say, that's going to create indoor pollutants that need to be vented out. Our furniture, our rugs, all these things are contributing, and so that's why we need mechanical ventilation in today's spaces, especially given the fact that we're building our buildings tighter than ever, right? And we're spending more time than ever in them. So under the category of mechanical ventilation, then, we've got the need for spot source dilution, that's bathrooms, kitchens, and we've got the need for whole home dilution of pollutants. That's where the energy code comes in and requires whole home continuously operating mechanical ventilation, which we'll get to in a minute. ASHRAE standards 62.1 and 62.2 address this need for mechanical ventilation in particular. 62.1 non-res, 62.2 residential, and then Title 24 effectively adopts these standards and puts it into the Title 24 code with a few minor adjustments. So this is code in our state and 3C run territory that we have mechanical ventilation. So when the CEC increased required mechanical ventilation last code cycle, actually the code cycle before, here was their quote: "Increasing ventilation rates will reduce respiratory illness and associated sick leave, reduce sick building symptoms, and increase productivity." That was their justification for doing so. And I want to focus on that increased productivity part. Other parts are important too, but a Harvard study recently, a few years back, put Harvard students in a lab environment and varied the indoor air quality and measured their performance on cognitive tests. So this, to my knowledge, was really eye-opening to see a quantitative analysis of the impact of bad indoor air. And they found, these three charts on the right show what they found: CO2 levels along the x-axis, and their scores on these cognitive tests on the y-axis on information usage, breadth of approach, and strategy, some of the more significant cognitive skills. They found as they reduced ventilation and increased CO2 concentration, people's ability to think and perform these higher order analysis tasks dropped by 60%. Wow, I was shocked when I read that. And it's just not something that's common knowledge. And when I think about we're building houses with home offices in them, where people are really going to need to perform high order cognitive functions, not to mention just doing your taxes at the dining room table or your kids doing their homework. This really was what got me thinking about improving IAQ. And here's a slide from one of my Energy Code ACE classes on spot source mechanical ventilation, specifically kitchen range hoods. This is a mandatory requirement new for 2022. And you'll see that it sets higher minimum airflow than in past code cycles. Used to be 100 CFM met the standard. Now it's up to 280 CFM. And this table below, you'll see, asks for higher airflow over natural gas ranges than electric ranges, in recognition of the fact that gas ranges produce additional pollutants relative to electric ones. You'll also notice something kind of confusing, maybe you wouldn't immediately grasp. There's higher CFM requirements when you have smaller dwellings, right? Normally we think of, okay, bigger house needs more ventilation, and that's true for IAQ. But for these spot sources, we need higher ventilation when those pollutants are concentrated in a smaller unit than when they're spread out, diluted over a larger building. So this is a good, for you energy consultants out there and architects, this requirement is good to highlight on your plan set to make sure it's not missed, to make sure adequate airflow is built into the kitchen range hood. Okay, so Title 24, ASHRAE 62.2 requires continuously operating mechanical ventilation systems for indoor air quality for the whole house, not just spot sources. And we can accomplish this. These three methods are treated equally by exhaust, supply, or balanced ventilation. And the vast majority of homes in California are using the exhaust-only method. The picture on the right shows an example of that. That bathroom exhaust fan, wired to run continuously, is producing the indoor air quality airflow for the whole house. And I ask you, if you picture this floor plan rambling 3,000 square feet, let's say, how well is that really spreading fresh air throughout the house? The answer is probably not that well, right? So for that reason, supply ventilation is a little bit better, and balanced ventilation with RVs, much better. We'll talk about why that is. Now, let me get to that question here in a second. So here's a depiction of the difference between exhaust ventilation and balanced ventilation with the heat recovery ventilator. On the left, we've got that example in the picture we just showed. We've got an exhaust fan. It's blowing a certain CFM of inside air out. And these squiggly arrows are an attempt to show it's being replaced by an equal volume of outside air from all different places across that building envelope. Could be the crawl space, it could be the walls, it could be the dog run, the garage if it's attached, the attic. So it's largely uncontrolled. It's not filtered, except that it's coming through the building envelope, so it's possibly being filtered by your insulation until it hits your return HVAC grill, right? And so as a result, we've got negative pressure in the house. Balanced ventilation, on the other hand, has equal supply CFM and exhaust CFM, so it maintains neutral pressure in the space. And you see we're showing the HRV located in the attic here, venting the stale air to the outside, bringing in fresh air from the outside, and then delivering that fresh air to the building and removing stale air from the building. And we've used that crossing paths icon there to indicate that we're exchanging the heat between those streams in that system. Okay, Judy brings up a question, well, a comment that you're not necessarily going to have neutral pressure in a house because there's outside forces acting on it. Absolutely true. Wind forces, for instance, causing infiltration. In the absence of that, we've got neutral pressure, right? When we've got wind acting on it, we've got slightly positive pressure. In the exhaust scenario with wind, we've got no control over what's going on. So the point remains that by having balanced ventilation, we've got a far superior control of the building envelope and the outside air that we're bringing in for IAQ. Thank you for that. So how much ventilation? Well, the 2022 Energy Code incorporated ASHRAE 62.2 into the residential standards and this is one of several equations used to calculate it. You notice it's based on the floor area. So the more floor area, the more CFM required, and the number of bedrooms, which is an approximation of the number of occupants in the space. And we've calculated this for a typical 2,700 square foot home in the chart on the right. You see it varies by climate zone for the point Judy just brought up. There's different wind expectations and thus different outside infiltration expectations by climate zone, which means that the mechanical ventilation fan has to do a different amount of airflow, even though this equation comes up with the same number. That's because Q tote is the sum of Q infiltration and Q fan. And what's going to show on your CF1R is the Q fan value, which shows up generally on the last page before the signature page of your CF1R report. And it looks like this. In this case, we're showing exhaust only ventilation. So this is default. And you see that 84 CFM that's required for this particular home. So that's a lot of airflow. What's the minimum here? 85 and up to almost 100. A single bathroom exhaust fan, probably not capable of moving that these days. So you're looking at 2 indoor air quality fans, 2 bathroom fans running continuously to meet this in most homes today. And an HRV can meet this with a single appliance. And the HVAC system, all this outside air is being brought into our space, right? Well, our HVAC system has to condition that air. So in the exhaust scenario that we showed earlier, right, this bathroom setup, let's say we're bringing in 90 CFM of outside air. That's 90 CFM that our HVAC system has to heat and cool. When it's 100 degrees outside, that's a significant amount of air to cool. When it's 40 degrees outside, that's a significant amount of air to heat. That's where the energy savings comes from with recovery ventilators. And all that is happening in your energy code software beneath the hood. So, You're going to get a useful estimate of energy savings when you put an HRV in your building.
And
So,
Nick, there was a question that came through from Mike. He's wondering how RV replaces air throughout a home. Is it a single point intake output, or is it incorporated into existing ductwork?
yeah, the best practice is that it's got dedicated ductwork to move the air where you want it. And we'll cover that in a minute. But from an energy code standpoint, the energy code doesn't care how you distribute that air, the supply, and the exhaust. It just wants balanced ventilation with heat recovery. So there's a number of options available to you, and we've got a slide coming up on various configurations. So hold that thought, Mike. Thank you. So I added a slide on COVID-19 because I think we've got more fertile ground to sell indoor air quality upgrades than ever before after COVID-19. I think you'd all agree that your clients have a long lasting memory of that period when we were concerned about going into spaces. We started to wonder more about air filtration. For instance, my daughter doesn't wear a mask on airplanes anymore. No comment. But she's sure that the air filtration systems on those long, narrow tubes are going to keep her safe. I told her, in my professional opinion, I strongly disagree. But we started thinking about these things more than ever. And so some building owners chose to set their airflow rates higher than code minimum, more dilution in their spaces. Others upgraded their return filters from MERV 6 to MERV 13. Filtering that return air made a lot of sense, especially since MERV 13 filters pull airborne bacteria and viruses, particles in that PM 2.5 size range, out of the air effectively, whereas 6 and 8 don't. And then even air cleaners and UV lights started to really gain traction. They'd always been around, but I would argue that we can sell these types of systems that have enhanced indoor air quality benefits better than ever. This study that I show here found that just setting ventilation to code minimum CFM was equivalent to vaccinating half to 60% of the occupants against the flu in terms of preventing flu. Wow, right? So just our HVAC equipment is equivalent to vaccinating half the people. That's a striking finding, I thought. Another webinar I sat in on during COVID I want to share with you was this awesome woman, Stephanie Taylor. She's a doctor. And she threw out this quote that shocked me. You building designers have a bigger impact on health than we clinicians. How about that? And she said she's founded this 40 to 60 RH advocacy group advocating for relative humidity in buildings between 40 and 60%. Because she said in her hospital, she discovered that is a magic zone. And it backs up other research like the Sterling chart you might have seen, but in a really nice real world way, I thought. She said, the darn architects put wood on the walls of our hospital. It was peeling off the walls because it was dry in there. We added humidity to keep the wood trims on the wall, and by accident brought down infection rates. I thought that was a really cool 3M Post-it note type example of how managing indoor air quality, in this case, humidity of indoor air, can have a significant impact on health and performance in our spaces. So you might wonder, well, how can I know if my indoor air quality is between those zones? Well, I've got some pictures coming up on indoor air quality monitors that I personally used to evaluate Well, it's one of the things that pushed me towards recovery ventilators in the first place, but then I used it to evaluate results, and I'll be sharing some data with you on that too. Um, you might find your particular part of the world stays in that zone and you don't have a big issue, but you might find, your indoor air really deviates from that large parts of the year, and therefore, it's worth managing. Now, a slide on E versus H was warranted. And I find that, we're all analytically minded, and we often ask the question soon after learning about recovery ventilators, well, do I need an HRV or do I need an ERV? The difference is ERVs have the membranes that when we cross the airstreams, they do the energy saving part, but they also allow moisture to transfer between the streams. So the humidity of the exhaust air influences the humidity of the incoming air. That's the key difference. Whereas HRVs don't swap moisture, ERVs do. Title 24 doesn't care. You don't even have to tell the energy model if you have an ERV or an HRV. So if it's compliance credit you need, don't worry about it too much. But your occupants might care, and we have a responsibility to specify these systems as completely as possible. So I would say in general, mild climates, HRVs better, other climates, ERVs better. And I quote my favorite building scientist here, Allison Bales, who does a really nice job. If you haven't followed him, Energy Vanguard is his company out of Atlanta. He's got this new book out. And he said the choice between ERV and HRV should land on ERV most of the time. He's in Atlanta, so he's got a lot more humidity to deal with than we do out here. But he said it's only in mild climates, not too cold, not too hot, not too humid or dry, where HRVs make sense. So I think this is something for you and your HVAC and your sub and your client to evaluate the particular climate you're planning to install in and make an informed decision, maybe consult your manufacturers. But I put an HRV in the main house and an ERV in the ADU, and I don't see appreciable difference in how they function here in climate zone 6, a couple of miles from the coast. Anything to tend to, Sarah, before I transition here?
No, nothing new in the chat.
All right, great. Let's get into the nitty gritty. So they're providing fresh filtered supply air, they're exhausting the stale air, and they're accomplishing heat recovery. That's what these systems are doing. And I thought Fine Home Building had a really nice cutaway diagram showing this, and this might help Mike picture it. This is the best practice for installation. You see we've got and hopefully you can see my cursor. Can you, Sarah?
Yes.
Okay, great. Let's start. The fresh air is coming in through this intake, through the building envelope, and coming into our heat exchanger core. The blue is the continuation of that supply air. And in this case, we're showing it blowing into a bedroom and into a living room. Of course, it would also, have some other rooms, but you see how this is a dedicated duct system for the supply air to get it in the places we want it in the house. Those are generally 4 or 5-inch ducts that they can be flex duct, they can be sheet metal if you really want to minimize pressure drop. But I found, in most reasonable size homes, flex duct was adequate and certainly a lot easier to handle in retrofit applications. The exhaust air is being expelled from the house here through this pink duct, another penetration through the building envelope. And you can see it's bringing in exhaust stale air from the kitchen and a bathroom in this picture. And in the core here, we're swapping the heat and or the moisture of those air streams, but without mixing them, So if you've got a cooking odor coming in the exhaust from the kitchen, you don't need to worry that that's going to show up behind closed bedroom doors. The air streams don't cross, they just swap heat and or moisture. So here's a zoom in on the unit itself. We're bringing in fresh air. We know the location we're bringing it in from, as opposed to exhaust ventilation. It's filtered, and most of these come with a really low grade filter just designed to catch insects. But you can't, I put a MERV 13 filter in the supply leg of mine. Not only is that Title 24 required, but it's a darn good idea, even if it weren't to require you, because it's going to pull out diesel particulates in the outside air, smoke particulates, etc. And then the stale air is coming in the upper right in the box here and swapping heat with that stream. So let's look at the heat recovery part in maybe these numbers will help illustrate the concept. In winter, let's say we've got a 40-degree day. We're bringing in that 40-degree air. In an exhaust-only scenario, that would be a burden on our heater, right? We're bringing in all that air at 40. Our house is, let's say, 70, the return air to this stale air. And so instead of that outdoor air coming in at 40, it's get tempered through the heat exchanger core with the 70-degree air, and maybe it comes into the house at 60. That's a 20-degree delta that our HVAC system doesn't have to deal with. And now the exhaust air is going out at 50. In summer, that outdoor air might be 100, might be a little warmer in the house, so that fresh air gets tempered to 86. So that's what? 10-degree delta for our cooling system to manage. So that's where the energy savings comes from. Here are my RVs. I would freely admit they're not HVAC contractor caliber installs. These were both, well, the one on the left was retrofit in the main house. The one on the right was new construction in the ADU. I'm not an HVAC contractor expert. I did the best that I could. Okay. But you can see the ducts. Upper left is the outdoor fresh air. Lower left is the outdoor stale air. Upper right is the supply, is the exhaust, and lower right is the supply. And then I've got those ducts snaking off to various points in the house, which I'll show you a diagram of the middle in a minute. The one on the right is the one for the new ADU. And so in its case, all the duct connections are on top, so they're in the drop ceiling above. And then they have a pant leg boot fixture for the outdoor penetration, so that there's just one penetration needed and it splits the air streams, which was pretty clean. Both of them have hobo monitors to monitor the temperature of the air streams.
And Nick, there was a question that came in just asking about accessibility. It says Title 24 compliant software has a checkbox that requires all supply filters, outside air inlets, RV recovery core are accessible. And
right.
Mark is asking if this is pretty typical.
Yeah, and absolutely critical. So I have to climb up in this attic and change the filters and check to make sure everything's working right and clean out the recovery core. That's not ideal. If I were designing a new home with a recovery ventilator, I'd put it down in a laundry room or a closet or a garage where I could freely access it. Good question. And we'll talk about that in the compliance portion, but to preview it, if you're not able to check that box, your compliance credit disappears, is neutralized. So that's an important box to check. But the one on the right is in my garage for precisely that reason. And I don't want to bother my tenants upstairs, so I just go in there and open that door. It's on a hinge, and do the maintenance I need.
And then Michelle just asked a question about that. How often do you change the filter and clean them when it's located in the attic?
Well, it may be located in the attic, but all the air streams are not from the attic. So it doesn't get attic air. It's well sealed. But I get up there every 6 months at the latest, and every quarter as a best practice. And I find that most of the time the filter is reasonable at that, in that window. The one on the right had a bug infestation last time I did it. I shouldn't say an infestation, but where our particular port was, it had sucked in a few mosquitoes and stuff. And so I just had to vacuum those out. And that's why you have to do it periodically. Yeah, good questions. And let's get to the local exhaust requirements when we get there. Okay. So I've gone to great pains to monitor these. And here is the one from my main house. No, sorry, this is the ADU. You'll see it's running at 60 watts. And those little blips, this is about a week period in June and July of this year. You'll see the little blips are when the humidity sensor is tripped by cooking, showering, whatever, and goes into boost mode to quickly remove that moisture, which was a really nice feature of that particular unit that I liked. And then it drops back down once the humidistat's met. This ERV runs at 60 CFM, 60 watts. That's not especially efficient. It's not an ECM efficient motor situation like some of the best in class systems, which can get down more like 0.6, 0.5 watts per CFM. This is operating at 1 watt per CFM, so it's not by any means a best in class unit. So I wanted to show you that. Now let me show you the temperatures from those hobo monitors. The blue is the outdoor fresh air, and this is a period from June to December of 2022, so about 6 months. So you can see that in winter, we're dropping down below 50, say 46. That's right here. And in summer, we had some days up in the high 90s, outdoor air. But the red is the supply air to the inside. So can you see that in winter on these 40-ish degree days, the worst we're doing is bringing in outdoor air in the mid 60s, right? So that's this area under the red is the savings to our HVAC system. And in summer, on these really hot days, the worst we're doing is, well, high 80s, one day in the low 90s. So this area in blue is the savings in summer. Why are the savings in summer so much less than the savings in winter, you ask? I'm glad you asked. Because the fans, and there's 2 fans in that box, are not 100% efficient at moving air. They create some heat. So RVs are tempering the indoor air, but also adding some heat to the airstream. And I've come to believe that that's why they perform a little better in heating season than cooling season, and thus they perform better in climate zones with more heating demand than cooling demand. And you'll see that our modeling data lines up with that. But you can also see with these red lines, really nice tempering actual data. Yeah. I thought that was pretty cool. First time I ever looked at that. How about indoor air quality? That's one of the main reasons we're doing this, right? Well, here's the ERV. I monitored the ADU's indoor air quality. I asked them to leave the monitor plugged in. And this is a period, December 2022 to January 2023, so about a month. You can see most of the time we're maintaining CO2 concentrations under 800 parts per million, which I would argue is a really good target to have. But there are spikes up to 1400 on one day, 1200, 1000 on other days. Probably they've got the windows closed, they've got extra people over. This shows the need for boost mode or opening your windows. And that's when you see the line drop like a stone, that's when they open the windows. So I thought that was really interesting to see too, that this ERV really is doing a nice job, even in winter when the windows are closed generally, of maintaining indoor air quality. And the last chart I wanted to show you, this is from the main house one. Remember I said RVs with dedicated duct systems do a nice job of getting fresh air behind closed bedroom doors at night, which an exhaust-only ventilation strategy obviously doesn't. Well, this shows we're maintaining CO2 spikes behind our bedroom doors. This is my master bedroom, sorry, primary bedroom, under 800 parts per million. And that's after we installed a recovery ventilator fresh air duct in our bedroom. Before that, I saw CO2 levels spiking to 1,000, 1,200 CFM as we slept at night. And, you know, studies show you're going to have a better quality of sleep if you can avoid those spikes. Hard to quantify that impact, but I think it's safe to believe it's there. So I wanted to show you a picture of one of these indoor air quality monitors in case you think, how do I know if I need to look at my indoor air quality? Well, answer one to that is get a meter like this. This one's called Aware. It's about 200 bucks. The other one I have is called Yoo-Hoo, about the same price, a little bit more. That one also measures nitrogen oxides, which is helpful if you're trying to evaluate whether a gas stove is polluting an indoor space. So if you sleep okay, if you work okay, if you seem to stay healthy, those are clues your indoor air quality is fine, right? If any of those maybe is a little out of whack, well, maybe it's worth spending the $200 on a meter and evaluating your indoor air quality. By the way, Lawrence Berkeley Labs found that these cheap meters are accurate enough and similar enough to the results they get from their $10,000 fancy research models to use in homes. Okay, one more note on CO2, because I found the science is unsettled here. Mauna Loa is where we measure the Earth's overall CO2 concentration. It's at about 420 parts per million. So that's what you're starting with. The Harvard study used 950 as typical indoor levels and 1400 as extreme. I sat in on a webinar by the sustainability woman from CBRE, and she said they're trying to achieve 800 parts per million in their high performance buildings. And Title 24, the non-res standards use outdoor concentration plus 600 parts per million as the trigger for demand control ventilation. So there's some data points for you to consider on how much is too much. You know, I would argue if you can keep it under 800, great. If you can keep it under 1,000, you're probably fine too. But it depends on the person, right? One more case study before I present the energy savings. During COVID, my daughter was in high school and she had two friends come over for a COVID classroom in this very office. And of course, 2 p.m. came around and their energy level dipped. And so I put the energy monitor in here and I found this. This is a typical school day. And you can see CO2 spiking to 1400 parts per million by about 11 a.m. And I thought, well, that can't be helping, right? I can't say it's all the entire reason why they're putting their heads down at 2 p.m., but it's certainly not helping. And so that was what prompted me to put my first HRV in. I put 30 CFM into this room, and that kept CO2 under 1,000 parts per million. So I counted that a victory. All right, looks like we're good on the chat. Yeah, Ryan, that's the holy grail, isn't it? Connecting those sensors to your RV and your HVAC system. I do have some RVs that have integrated sensors that I'll talk about, but no, I haven't actively integrated them. But that's what we need to get to. So how much energy can they save? Okay, the small planet supply study, the SoCal gas study, I've selected some of the key findings here to share that with you. And next we'll talk about compliance savings. I think we're doing pretty well on time. Yeah. So we found typical recovery ventilators, that is not the best in class. These have watts per CFM in the 0.7 to 1 range. These have recovery effectiveness in the 70% range. We found energy savings of 11 to 15% in climate zones 1 to 5. So that covers most of 3C REN's territory, right? Which I would think of as 4 and 5 versus exhaust only ventilation. The best in class ones boosted that 21 to 31%. These are units with better than 0.7 watts per CFM and 85-90% recovery effectiveness. So there really is a case for looking at these high performance models. They make a big difference. In other climate zones, we found 10 to 14 and 16 showed lower savings than this, than 1 to 5, and 6 to 9 and 15 were less well suited for energy savings with HRVs. So how are we getting to these? There's an inherent trade-off here. A typical recovery ventilator with, well, a typical exhaust fan strategy might use 28 watts continuously for 80 CFM, whereas the recovery ventilator has 2 fans running concurrently, might use 56, let's say. That's an extra annual ventilation energy of 245 kilowatt hours. So that's our penalty we're starting with for upgrading our indoor air quality. I would argue it's no penalty at all. You're potentially improving quality of sleep and cognitive performance, and your home office is going to work better and all that, right? But let's say that's our investment. And if we're in climate zone 5, there's really no cooling energy savings to speak of in that climate zone. Some of my models don't even show cooling energy use in climate zone 5. So it's all heating energy savings. And in this case, maybe that's 290 kilowatt hours. So we come out 45 kilowatt hours ahead. But with a best in class version, we're reducing that recovery ventilator energy to 40 watts continuous. So we've only got 105 kilowatt hours penalty, and we're saving more because of the better recovery effectiveness. So we might come out 290 kilowatt hours ahead. So you see how the best in class math is working. And here's a chart. It's in your handout, so you can dig into it a little bit more deeply. But this was our findings for a typical RV in a 1-story home with a heat pump. You're going to get actually better savings on an MMBTU basis with a gas furnace. But I put in the heat pump table because I think that's where we're all headed, right? And you see that in the last column, the ventilation savings are negative, because of what I just showed you. We've got added fan energy for the balanced ventilation RV compared to exhaust ventilation. That's what we're comparing here. But we've got heating savings and cooling savings in some climate zones. So the HVAC savings kWh in the second column is the sum of these other columns. This is the bottom line. And so you see climate zone 1, 2, 3, 5, 11, 12, 14, 16 with savings. You see that? And on a percent basis, yeah, 3, 7. It was a little better in the furnace chart. But thank you, Sarah. She put a link to the study in your slide deck, so you can look into it in more detail. Here's the chart of a best-in-class HRV in that same house with a heat pump. Look at the difference. Now climate zones 1 through 5 are all big winners, over 200 kilowatt hours in savings, and 10 through 16 look good now too. So there's a link to that study as well. Difference in average cost. It's several $1,000s in most cases from my experience. Yeah. But some of those best in class ones, I'm trying not to talk too much about particular brands, but Zender in particular has accessories for the distribution of the air that look like they really make the process simpler. I had to design my duct systems myself and buy the sheet metal duct and the flex duct, and I had a HERS-Rater friend do the duct design for me. So there are added benefits that you get for that cost. You also get some functions for that cost, and probably fault indication display as part of that bargain too, which, as I'm going to show you in the next section, boosts compliance credit. So in answer to the question about integrating your sensor data to your RV function, we found, this CERV, this guy's out of Chicago. I don't see it in our market much, but I'm fascinated by it because it does have CO2 sensors that adjust the ventilation delivery according to the demand in the space. This runs almost counter to California's energy code, which says, I want a continuous mechanical ventilation system for every new home. But I would argue this is smarter because when you're not home, you don't need to eat that extra energy. When you're on vacation, you don't need to eat that extra energy. And some of the time you want extra energy, you want extra airflow. Makes all the sense in the world. Other systems like my ADU one has a humidistat driving a boost. Others have manual boost mode. And then ventilation cooling via bypass mode. As part of our best-in-class study, which you'll see if you look at the study, we tested what would happen if an HRV monitoring outdoor air temperature would shift to 100% outdoor air when that was favorable to the energy balance. That is, don't exchange the air from the inside when it's not favorable. Just bring the outside air in when it's nice and cool, like a whole house fan does, right? And we found in climate zone 5, 50 kilowatt hours additional possible for that function like those Zenders have. So that's a good feature to look for, especially in mild climate zones. All right, which brings me to another Slido check-in. So if you can go back to that, I want to ask you, what is the trade-off we're making with recovery ventilators? And we're going to get into compliance credit next. Yeah, you got it. You know, I'm like you, I'm always, my guards go up, my alarms go off when someone's trying to sell me something with no drawbacks. So it's good for us to go in eyes open with the fact, hey, we're going to spend more money to better ventilate this building, higher ventilation energy usage, but we're counting on, by tempering that outside air, energy savings to offset that. But I would argue, even without those energy savings, the ability to make it balanced ventilation, filtered, better distributed, would likely justify the expense. Okay. Yeah, and Ari asks, what about the energy difference between balanced ventilation? Because I should have said that. A recovery ventilator is one enhanced form of balanced ventilation. Balanced ventilation means supply and exhaust within 10% of each other. And so you can do balanced ventilation without heat recovery by just pairing an exhaust and a supply fan, right? And so, yes, RVs will have slightly higher energy use than a balanced ventilation system because of the pressure drop. Typically, a balanced ventilation system is going to not have the same ductwork snaking throughout the house. But if it did, it'd be pretty darn similar. Little extra pressure drop in the heat exchanger core, though. Yeah. Okay, so let's talk about the code compliance picture. The answer is they're super powerful. And those of you who are energy consultants, Lanny and Sarah online, know this. Typical efficiency EDR impact of 10% with the highest climate zones 1, 2, 3, 5, and 16. And 4 is not bad either for you central coasters. Best in class recovery ventilators can boost that average impact to 14%, so quite a bit. And notice it's helping source EDR as much or more than it is efficiency EDR. That source EDR score is sometimes hard to rein in when we're using gas furnaces and gas water heaters, so HRVs might be your answer on some projects. So this chart is showing that efficiency EDR impact. Recognize that our target for that is often about 50 points. So when you look at a efficiency EDR impact of 5 points, for instance, well, that's 10%. In climate zone 16, the Sierras, you're looking at 10 points, 20% impact. So it's major. One of the best buttons we have to push. Now, multifamily is different because Title 24 already requires balanced ventilation in new multifamily units unless the builder goes to the trouble of blower door testing all the units. So I definitely advise my multifamily clients to choose that balanced route. So that means the ventilation penalty is effectively zero. And all the cooling and heating energy savings are going to the bottom line. So the compliance impact's even a little bit better for multifamily, as shown here. So a few quick slides on how to do it in the software. I'm using CBEC screen catchers here, but the same is possible using Energy Pro and the other software. On the left, your model is going to default to exhaust ventilation without any intervention. And you'll see this IAQ tab up at the top of the model is showing you minimum IAQ ventilation based on your square footage in bedrooms and climate zone 60.4 CFM, right? Now, when we add the recovery ventilator in the right side screen, notice the minimum IAQ ventilation drops to 53.3. That's because balanced ventilation gets a slight recognition for the fact that it's better for indoor air quality than exhaust. in a slightly lower target for the same house. In this case, I put in a 55 CFM HRV, although I'm sorry, it's labeled as 50 CFM here. And here are the two checkboxes that some of you were mentioning. The first one is all supply air filters, etc., are accessible. That box is checked. If that box is not checked, you're going to get 0 compliance credit. That's what the ACM says. That's what I've seen. So make sure that you, 1, design it that way, and 2, check that box. Now, the second box is it turns on or off a derate function. If you click that box and your system is equipped with a fault indicator display, and those that's defined in the RACM, you avoid a 10% penalty on watts per CFM and a 10% penalty on recovery effectiveness. If that is unchecked, if your system does not alert the occupants to the need to change their filter or a problem with the unit, you get those 10% derates. So you're not getting the full compliance benefit of your system. So that's what those 2 boxes do. So what happens beneath the hood when we add a recovery ventilator? Well, the energy code has taken this position that is advantageous for recovery ventilators that says, if you want to add extra indoor air quality to a space, we're not going to penalize you for that decision. And I think that's fair because, as I said before, the science is unsettled a little bit on how much ventilation is enough. So you're going to tell it, in this case, 55 CFM, 0.7 watts per CFM, 67% SRE. So it's going to model the house with the airflow you enter, the watts per CFM you enter, and the outdoor air will be at the temperature calculated using that recovery effectiveness instead of the outdoor ambient. The standard design is what creates our credit. Whatever the airflow you entered is the standard design up to 125% of code minimum, which, if you remember, was about 53 on this house. So if you exceed 125% of 53 with your airflow, you're going to get no additional compliance credit. In fact, it's going to start hurting you. So remember that 125% magic number. You want to maximize your compliance credit, that's probably where you set the CFM. The standard design is going to have a default 0.7 watts per CFM, and the outdoor air is going to come in with no heat recovery. That's where we open up our compliance margin. So let me give you an example. This is from a project I just did. It's 6 duplexes in LA, climate zone 8. The original compliance models I did for them had the VCHP credit. That's really strong also, average 5% impact. For ductless mini split heat pumps, it had an upgraded gas tankless water heater. The builder completely spaced and missed those features. Have we heard this story before, folks? Yes. They used a ducted heat pump, not the VCHP compliant one, and a standard gas tankless, and asked me to fix their problem. You guys heard this story before? So I sent them this email. Hey, I did what ifs, and I see 2 options for you. Add rigid foam to the walls and above roof deck insulation, or add an HRV. And I talked to them about what that meant. You need to find space for the ducts. You need to find space for the unit. They also make through the wall units, which I'll show you in a minute. So they said, okay, we'd prefer the HRV. And here's the before and after. Before, we were 1.2 efficiency EDR points away from compliance, as shown on the left. After, we were 0.3 better. So literally, HRVs, and this was not a best in class unit, 72% and 0.6. 0.6 is pretty good though. Heck, HRVs solved our problem. Right, Michelle? Yeah. So the bottom line on compliance is these are like that big red Staples button to push, right? These are one of the best compliance changing options we have, along with VCHP, along with battery storage systems. Okay, a few notes to finish up on specifying these to make sure your project works. Because we have to be the recovery ventilator doulas, the gurus, the coaches in all of this, or it's not going to happen right. Here are the questions, some of the questions we need to ask. Where's the unit physically going to be located in a way that's serviceable, in a way that's adjacent to all the spaces you need to ventilate? What are the routes for the ducts you can take? What are the CFM you need by room? Now, you don't have to define CFM by room when you specify the unit, but by the time they install it, they do, right? And duct routes and location, I would argue, are some things you do need to think about before you specify them on the project. Where are the supply and exhaust registers going to go? I generally look at a floor plan like this one and say, you know, this happens to be my main house install, and I had Dov Cameras, some of you probably know him, do my duct design. And you can see he's got some 6-inch, some 5-inch, some 4-inch ducts shown, and we split up the CFM together. We chose to ventilate the green zone of the house because we couldn't get the ducts across to the yellow zone. So we only got fresh air behind one closed bedroom door and the office, which is the lower room down the bottom. We also need to think about how are we going to get the outdoor air in, where are we going to penetrate the envelope, and how are we going to get the stale air out? And where are we going to put the occupant controls for this thing? Especially if we've got an FID panel. Now, some of those might be a smartphone based, so you don't need a panel, but you need to think about that. You certainly need to think about filter changes too. So these are some of the things to work through with your clients before you just throw an HRV into their model. Now, I talked mostly today about the dedicated distribution duct approach, which I would argue is best class, but there are other options. The Zender model on the left is a through the wall unit. It's capable of small CFM, I want to say about 30 or 40. So it's not, you might need several of these for a house, but you don't need any ductwork. So those are pretty cool. The one in the middle is a paired system. So you put in pairs of these and they alternate airflow direction with a ceramic core to store the indoor air temperature. Pretty nifty. Also, you need several pairs for a whole house. But when you don't have room for the ducts, these may be the only way you can do it. And then you can also install your HRV, not with dedicated distribution systems, but shared distribution systems with your HVAC system. So you can duct the stale air exhaust out of the return air and duct the fresh air supply into the supply air. I don't think that's optimal though, because, you know, it means your HVAC system has to turn on its main fan if you duct into the supply. It means your duct system really isn't optimized for the level of airflow of your recovery ventilator. And those are main problems because you don't know where that supply air and stale air is going to come from if your duct system isn't designed right. So I put it up there as an option, but it's one to be used carefully. A note on other benefits. This is my ADU. I built it out of SIPS panels. And I would say the combination, which we're increasingly using, ductless mini splits, we take the VCHP credit, and recovery ventilators, they allow for vaulted ceilings like nobody's business because we don't need an attic for our duct space, right? Or the mechanical system up there. We don't need a bathroom exhaust fan because, and this was a question earlier, if we put 20 CFM of exhaust in a bathroom with our recovery ventilator running continuously, we meet the spot ventilation requirement. Don't let the building department tell you, no, you need a bathroom exhaust fan, minimum 50 CFM, because they're wrong. I had to show my building department the code language where this exists. So I was able to vault the ceiling in my bathroom. I was able to vault the ceiling in this whole ADU, which really makes the place feel better. So another nice benefit of recovery ventilators is that. And even if we go ducted mini splits, you don't want the high wall units, let's say, well, they can fit in a soffit. So that's a nice benefit. Where do we find these statistics? Well, the HVI directory is the best place. They list various recovery ventilators, their CFM, their watts, their SRE, their ASRE, and that's a reliable place to go to find your numbers. So let me ask you one final Slido poll before we take Q&A. What are your takeaways? Any surprises? Hopefully you're going to use these more often. Any lingering concerns? Come on. I promise I didn't enter that. Sarah, was that you?
I wish.
I find it's a compelling argument. And, you know, I don't always have an hour and a half to spend with clients to go through all these benefits with them. So I wish I'd use them on more projects. Concerned about getting clients to use them. Yeah, why? Healthier indoor air quality, more consideration. Yeah, best in class recovery ventilators really make a difference. Okay, more valuable than you thought in 16, yeah. And one voting for putting one in their home. Love that. Yeah, whoever said concerned about getting clients to use them, I'm interested in your perspective there. What do you think the pushback's likely to be? Feel free to put it in chat, or we're at the point where we can take Q&A and do some unmute yourself. Although, Sarah, do you want to do your final slides before we do that, maybe?
Yeah, that sounds good. That way we can have the rest of the time for questions.
Okay. All right, let me go to that. So I would argue, to sum up, these allow you to be your most productive selves. Remember the Harvard cognitive study where even Harvard students perform 60% worse with bad indoor air quality. There's my email. I'd love to hear from you with your experience with these. And Sarah, how do you want to tie up?
Yeah. So I just want to reiterate that we have learning units available for this class today, both AIA and ICC. The slides and the recording will be coming to your inbox, as well as a survey. And along those lines, I'll just be launching a poll. This one is just our general poll, just to kind of gauge meeting usefulness. It just helps us inform future courses. And then we have a few, well, more than a few, upcoming courses in July and through, well, the end of the year. And all of these are links. You can click on them and read the description and sign up for them. The one down here, September 13th, is with Nick Brown. So definitely sign up for that one. Yeah, and with that, we can open it up for questions. Feel free to unmute yourself. And yeah, thank you.
Awesome. I'll add a couple of other dates. We have a new class for SCE, all electric for homeowners. That's August 8th and 15th if you want to sign up at SCE's Energy Education Center. And then our full class practical guide to all electric residential buildings is September 12th. So if you're interested in that all electric material, love to have you along.
Hey, Nick.
Yeah.
Hey, can I ask it? I have 5 minutes before I have to jump off and get on to a client meeting. We didn't really address RVs as they would be potentially set up into either an existing or new central ducted system. And I'm designing mechanical systems and designing HRVs and ERVs with these systems. And my biggest learning challenge is where to actually put the ducts. A lot of the information is about putting it into the return, but I don't believe these ERVs have enough fan power to overcome the static pressure between their filter of a MERV 13 and the MERV 13 on the air handler. And sometimes you can put that filter at the return grill itself. And so I just wanted to see if you had any information about connecting at the supply side in front of the unit. But my whole thing has been telling people you have to run the air handler 24/7 in order to use it through the ducted system, because it's only 80, 100 CFM trying to go through a couple hundred feet of duct work. So I just want to make sure I'm not out of line with this understanding, and that as you said, the best practice is its own ducted system. If you're going to do it into a centralized ducted system, you have to run that air handler, and you kind of negate energy savings at that point.
Yeah.
You're just fighting an uphill battle.
Yeah, I agree. So there is also a hybrid configuration where you pull the stale air out of the return duct, but you have ducted supply, dedicated ducted supply that gets around the need to run the central air handler.
Okay, cool.
But you're right
I'll
on.
touch base. Yeah, I'll touch base with you on a separate time enough. I just have to jump off. I'm going to personally try and do it. I'm building a passive solar off-grid house myself, and I'm going to try and I have a very small duct system, so I'm going to try it there. But I just kind of was just wanted to get to the point of that and see if I was missing anything key.
No. And thanks. Love to hear your perspective.
Yeah, cool. Thanks. And thanks for the presentation today. It was great.
Thank you.
Okay.
And there was a question earlier that came through in the chat, just asking if you could talk briefly about local exhaust requirements and which can be served by an RV or not.
Okay. Certainly the bathroom exhaust local requirements, I want to say it's 50 CFM. And that's not continuous. That's demand. You turn it on in the bathroom as needed. And so if that's continuous if it's continuous, that can be 20 CFM. That code language you'll find. I may drop it into chat for whoever asked that question after we're done here. But a recovery ventilator is not going to be sufficient to replace your kitchen vent hood, for instance. Those CFM requirements are far in excess of what a recovery ventilator can do. So you're still going to need that local spot ventilation. But to my knowledge, those are the only spot ventilation requirements. Hi, Michelle. She asked about temperature discomfort. No, and there's a little duct right here bringing 30 CFM in. It's never more than 85, and it's mixing with the rest of the air. It's also really quiet because it's that low CFM. And we got to realize that if that were a 100-degree day, we're bringing that air in whether we like it or not, with a ventilation fan. So the comfort should be better. But yeah, you do want to think about where you position the registers so that you get a little bit of mixing before it hits you in the face.
All right, and with that, we're at time. It's 11 o'clock, so just want to thank you all for joining us today, and thank you, Nick, for a wonderful and very informative course today. It's I know that I learned a lot too. So
Pleasure.
yeah, so the slides and the recording will be coming out in an email, and thanks again.
Thank you, Sarah. Thank you all for being here. It was awesome.